the moving coil galvanometer. So that is the moving coil galvanometer. Now before as you can see, there is a large diagram. So before I get into the diagram, I'll just go back 2 topics behind so that you will realize, you will just get a recap of what we are going to discuss here. So you can recall this diagram. We had a loop and we had these 2 permanent magnets. This was the north pole, this was the south pole, and this was the loop, and this was the axis, and this was rotating like this. So if you can recall this diagram, then you will be able to understand this diagram as well. Now before I get into this one, just some additions which we need to do to this diagram. The end product, the end result of this diagram was tau is equal to IAB, which we made it as tau is equal to M cross B, and that M was taken as I into A. That is the magnetic dipole moment. In this situation, we had taken a single loop. So a single current I was flowing from one side to the other side. The same current was going in this arm as well as on the other side. Now, if instead of having a single turn, if I make this coil to turn twice, instead of having this as a single loop, what I will do here is, I will make this to go around once again, then it will come out. Now, what I have here is, there will be 2 current conductors in front of the north pole and 2 conductors in front of the south pole. The current flowing, one I will be flowing in one conductor, and the same current I will be again flowing in the second conductor. Now, instead of having one current, we have 2 currents. So, whatever the torque we had, it will be twice, because the current has become twice, and also the magnetic dipole moment will be becoming twice, because right now the current is flowing 2 times the original value. Now instead of having just 2, I can make it 3, I can make it 5, I can make it 10, I can make it 100. As long as the number of coils are within the range of that magnetic field, I can increase the number of turns in this coil, and what I need to do here is, instead of multiplying this 2, I can just multiply it as n. That is the number of turns. The same thing is true with the torque. So this is going to be my equation for the torque. The magnetic dipole moment will also be increased n times, as well as the torque on that coil will also be increased by n times. When this coil was rotating like this, the portion which is right in front of this magnetic field and this magnetic field, it is going to get more intensity of the magnetic field compared to when it is rotating like this, and this region comes on the top and this region goes to the bottom. It is going to have less intensity of the magnetic field. So the magnetic field, no doubt, when we talk in terms of straight lines, it is going to be uniform, but when the coil is rotating, in some regions, the coil is going to experience a stronger magnetic field when the coil is right in front of the magnetic pole, and it is going to come across a weaker field when it is away from that is the magnetic pole. So when the coil is like this end is going to get a strong field, and this end is also going to get the strong field. But when this coil becomes like this, it is like, if I show the cross section, the coil looks like this. In this region, there will be strong field. When the same coil becomes like this, the field is going to be comparatively weaker. No doubt, the entire region, the magnetic field is uniform. It has got equal intensity. But when this is here, in this situation, the coil is going to experience a weaker intensity of the magnetic field. That is one concept. Then another concept here, which we need to understand, is that this coil, when it was like this, the current was flowing in this way, and this will be forced in the downward direction, which we have seen when we were discussing the force on the current carrying conductor. So this will be forced in this direction. This side goes in the downward way. At the same time, the other side, this is going to experience an upward force. So this side is going to turn like this. Ultimately, it is going to produce the torque. Now, when this coil becomes perpendicular to the direction of the magnetic field, that means it becomes like this, will it be turning further? No, the coil is not going to turn further. Let us assume that this side is the north pole and this side is the south pole. If initially the position of the coil was like this, it rotated like this. Now it has become in this way. It is perpendicular to the direction of the magnetic field. Is it going to experience any torque? No. Why? Because this coil, when it was carrying the current in this direction, the upper part, it was going to be like this. the current was flowing in this direction, the lower part of this coil is going to produce a north pole and the upper part of the coil is going to produce a south pole, because moving current or moving charges produce the magnetic field, and if there is a magnetic field, it needs to have a north side and a south side. So when this coil was like this, the lower portion becomes the north pole, the upper portion becomes the south pole, and when it turns like this, the south pole is right in front of the north pole, and the north pole, which was created on the bottom, it is right now facing the south pole. So there is attraction between those magnets. So when that happens, it is going to be in the state of equilibrium. When that equilibrium occurs, it is going to stay there for as long as the magnetic field is there and as long as the same quantity of current is flowing in that coil. Let us say, if this is the equilibrium position, still the magnetic field is from left to right. There is a current flowing in the conductor which is coming out of the board. There is still a force which is going to act in the upward direction. So this will be the force. Let us say this was F2 according to the diagram which we have seen 2 days ago. Similarly, on this one, there is a magnetic field which is going on. So left to right, the current is flowing into the board and the force is going to be acting in the downward direction. So this is going to be F1. So F1 and F2 are equal and opposite to each other. So there are no net forces acting either on this side of the conductor or on the other side of the conductor. Even if the forces are acting, they are equal and opposite. So they will cancel each other. So there will be no force and there will be no torque in this position, which we call it as the stable equilibrium. This kind of situation we have already seen in the electric dipole also in the first chapter when we had derived the equation tau is equal to E cross E. We had two equilibriums. One was called as stable equilibrium and one was called as unstable equilibrium. If the direction between the electric field and the electric dipole moment, if it was 0 degrees, in that case it will be the stable equilibrium. If the angle between them is 180 degree, in that case it is going to become the unstable equilibrium. I'll just show the situation. Let us say this is the electric field and this is the dipole. Let us say this is the -2 charge and this is the +2 charge. So this is already aligned and the angle between these two is going to be 0 degrees, and this P cross E, if it is going to be expanded, it is going to become PE sin theta, and this theta is 0, so the net torque is going to become 0 on this electric dipole. Now let us say, instead of having the +Q on this side, let us have the -P on this side, and the dipole moment is facing in the opposite direction to the electric field. The electric field is going towards right, the dipole moment is going towards left. Now the angle is 180 degree. They are both facing opposite to each other. In that case also, this torque becomes 0. When that torque becomes 0, still again it is going to create an equilibrium situation, but that equilibrium is going to be an unstable equilibrium. There is an area vector for this current loop, and where that vector is going to be facing, that vector is going to be facing in the downward direction where the north pole is going to be produced. In this situation, when that situation becomes like this, the area vector is going to be like this. So this is going to be the direction of the magnetic dipole moment, and at the same time I have shown the direction of the magnetic field from left to right. So this is going to be my magnetic field. Now if I come to this equation, that is tau is equal to m cross b, again it will be expanded as m b sin theta, what is the cross product. And when these two vectors are facing in the same direction, the sin theta, it is going to become 0, and when this becomes 0, the torque becomes 0, and that is going to give us a situation of stable equilibrium. Now, just like we had two equilibrium positions for the electric dipole, we will also have the similar situation for the magnetic dipole. What is that going to be? If instead of the coil becoming like this, the coil may become like this. That is, this side becomes north pole and this side becomes south pole. Now this m vector is going to face left and the b vector is facing right. So in that case also, we will get again m cross b, m b sin theta. Sin theta, it is going to be sin 180, and that is again going to give us a 0. Again it is going to give us a situation of equilibrium, and this situation will be an unstable one, because slightest disturbance, if the coil is like this, if there is a disturbance happening, then it is going to flip like this and it's going to come to the stable equilibrium position. Coil which we had here, it has got some 100 number of turns, maybe 500, maybe 800, maybe 1000. Some hundreds of number of turns are here, but these are wound on a circular iron core. There is a circular iron core. So the insulated copper wire will be wound like this across the axis of that soft iron core, and those turns are shown as straight lines here. The straight lines which we are seeing here, these are the copper windings which are called as coil. So this situation, this is going to be the central part of this moving coil galvanometer. Now on the top of that, we are going to put a pointer, and that pointer is shown here. And this pointer will be able to move over a scale. Coming to the magnets, we had two magnets, but the faces were flat, and due to which, what I had said, this region will have a stronger magnetic field and these regions will have a weaker magnetic field. Now, to avoid that, to make sure that the magnetic field is uniform, the faces of the magnets will not be kept straight, instead they will be made curved. So what I am going to do here is, instead of keeping this as straight, I will make it curved. And this side also, instead of keeping it straight, I am going to make it curved. So that is what you are seeing here. The north face is also curved, the south face is also curved. Now when this happens, what it is going to produce, the magnetic field is going to be like this and like this on the ends. Similarly, it is going to be like this on the ends. And when we place that coil in between, that coil and this iron core, they are going to experience a uniform radial magnetic field. And this iron core, which has got the windings on the top, this will be fixed over a spring that will have a reading of 30 on either side. This is 30 on the left hand side, again a 30 on the right hand side. The central one will be the 0 reading. And that pointer always rests in that vertical position, that is at the 0 reading. Now, when we pass the current through this coil, we will be having two terminals. When the current flows, this coil is going to get the moving charge, it is going to become a magnet, and this coil will turn either to left or to right depending on the direction of the flow of current. When that happens, let us say the coil has turned like this, it is going towards left. The pointer also goes along with the coil towards the left. So it is going to show some reading on the scale. As soon as we turn off the current, it has to come back to the original position, that is the 0 reading position. So for getting it back to that 0 position or the equilibrium position, that spring is going to give the counter torque, because when the current flows, there will be a torque produced in the soft iron core and the coil that is going to make this coil to turn. And when that current is off, if the spring is not there, it will stay there permanently, because this is connected, this is fixed in a such a way that it is always in the balanced situation. So even if it goes like this, it will stay there permanently. So what we want, it should not stay there permanently. So what we do here is we have to add a spring which is like a spiral spring. So as soon as the current is turned off, it will come back to the 0 position. This setup is called as the moving coil galvanometer. So let's get on the basics. What is a galvanometer? A galvanometer is an instrument to detect the presence of current and the direction of current in the circuit. It is going to perform two functions. It is going to detect the presence of current, that is the first function, and the second function is it is going to give the direction of the current flowing in the circuit. So our equation was tau is equal to NVA into I. You can rearrange the letters as you want, NABI or BANI, whatever you want, you can write it, or you can take it as alphabetical order ABNI or ABIN, but better keep it I, keep that I in the end. That's going to be, it is a small kind of a derivation for this one, and that will be for this spring. What is the job of the spring? The job of the spring is to provide the counter torque. The torque, one torque is going to be produced when the current flows in the coil, and the spring is going to produce an opposing torque which will bring the pointer back to the original or the equilibrium position. So the counter torque should be equal to K into phi. It represents the angle which it has moved from its equilibrium position. It can be towards right or it can be towards left, and that phi is always an acute angle. It is always less than 90 degrees. So these two torques should be equal and opposite. So if I want the magnitudes, I can equate them. K phi is equal to NVA into I. Now, I will rearrange this equation so that I get how much deflection will be happening of this pointer when a certain amount of current flows in that coil. So that means if I have constructed a galvanometer using some setup, I have used some permanent magnets, I have made some like 800 turns on the coil, and then there is a very lightweight soft iron core, and there is a spring which has a constant K. So what I can do here is I can write equation for the deflection produced in this pointer. So that will be phi is equal to NVA divided by K into I. Now I have put a bracket on the 4 terms. These 4 terms, if I have constructed the galvanometer, those terms which are inside the bracket will remain constant. What I can say is the phi is proportional to I. So that means using this galvanometer I can establish the relation between the current, and we can just get a rough idea of how much current is flowing in the galvanometer. Is it less current or more current? If there is less deflection, it is less current. If it is more deflection, it is more current. Now again I will remove this proportionality. I will go back to this equation. I will bring this I to the left hand side. So phi divided by I am going to get the 2 variables, and on the right hand side I will be getting the constants NVA divided by K. This equation is called as current sensitivity. It will be measured as radian per ampere. So this gives us the current sensitivity of the galvanometer. If there are more number of turns, it will be more sensitive. If it is less number of turns, the sensitivity will be less. Magnetic field also, if we use the stronger magnets, we are going to have more sensitivity. If we use weaker magnets, or over the time the magnets may become weaker, so again the sensitivity will be less. And area is mostly fixed, we cannot change the area. Once it is constructed, it will remain fixed. The same thing is true for the K, that is the spring constant. On the same lines, we will have a voltage sensitivity. So instead of detecting the presence of current, we can also detect the presence of a potential difference between 2 terminals in a circuit. We have Ohm's law, V is equal to IR, and I can rearrange it for I. It will become V by R, and I can use this V by R in the place of this I, so it will become phi is equal to NVA divided by K, and there is a V by R on the outside. I can shift this V to the left hand side. It will become phi divided by V. It is going to become NVA divided by K. I can use this R here, or I can write these constants as fixed and I will keep that R on the outside. So both ways it is going to be working fine. So this equation is called as the voltage sensitivity.